All right, I want to talk really briefly, a brief lesson about section 1.4. And what I'm wanting to refer to the slides that I had on in Sapling for sections 1.4 and 1.5. The 1.4 part of it, let's talk about that real quickly. I talked about several points of this in class on Tuesday. And the main theme idea is limits, talking about limits, trig functions, and the continuity of trig and exponential and log functions. Take a look with me. What we talked about in class a little bit was I went through the graph of a sine function and recognizing that at 0, the sine is 0. And at x equals 0, the cosine is equal to 1. We had talked about that. And I also worked through the idea of the limit as theta goes to 0 of sine theta over theta equals 1. We showed it by graph. I showed it by graphing that function sine theta over theta, and saw that at theta the function can't be equal to 0 because it causes the denominator to be equal to 0. But there's an open spot there, and the graph of it as you come in from the right, you can look at it in notes from the class. That as you come in from the right, you're going to 1. And as you're coming in from the left, you're going to 1. So the limit is equal to 1. The second one regarding cosine theta minus 1 over theta. That's used a little less often. I'm not going to be dwelling on that at all. We're going to ask you some things about the sine theta over theta, though, circumstance. So that'll be one to know. And here's a couple of examples. I did something similar in class regarding, I think it was 3 theta. But here's the idea. Theta is going to 0. Sine of 2 theta over theta, those aren't matching. 2 theta and theta aren't matching. We can't go in and just manipulate that 2 theta and make it into anything, but we can make that theta in the denominator. We multiply it by 2, we can make it match that value of the angle inside the sine function parentheses. So the idea is that if we can make that bottom denominator 2 multiply by 2, we have to counter that, multiply top and bottom by 2, so we multiply by 1. And as a result, now this matches. And this matching, the way they represent it in the text is, that, okay, so they're the same now. That 2 is out front, bring it out front. The constant time, a limit of a constant times a function is the constant times the limit. So we've got that drawn here. And you can see that then this goes back to that definition of the limit as t goes to 0 of sine of x, t sine of t over t. This is equal to 1. As a result, you've got 2 times 1 is 2. The second one, they do 2 steps. One of them is you got 2 different values in here, 3 theta and 4 theta in this situation. And what they do, they get them both to match, to become 1. So the idea is get this one to match what's in here with what's down here. They had to actually introduce the 1 over theta, multiply by 1 over theta on top, and multiply by 1 over theta on the bottom. You've got a tool to work with there then. And as a result, then once you have that theta, if you multiply the top and bottom by 3, you've got this circumstance that develops. These match. Now you can become recognized at the same value. Therefore, this is 1 and this is 3. So it's going to be 3 out front times 1 over 4 out front times 1. So you end up with the circumstance of being, you bring the 3 down and bring the 4 down, you end up with 3 times 1 over 4 times 1 gives you 3 over 4. All right, so that was a little step, a dance of some sort that you need to manipulate in order to utilize that rule that the limit of sine, as theta goes to 0 of sine of theta over theta equals 1 is utilized in some fashion. And I'll probably show you that a little bit downstream. One other point to make, though, the continuity of trigonometric functions. So recognize a sine function, it goes forever. The wave goes, it's not just 0 to 2 pi. It goes forever in each direction, and it's solid. There's no denominator. There's nothing causing this to be illegal, 0 in the denominator or anything like that. So it's continuous for all real numbers, and the same for the cosine function. Notice the sine starts out in the midline, and the cosine does not. The trivial point about the situation. Tangent, on the other hand, is defined by sine over cos, so it's got a denominator. and the denominator can be equal to 0. So it is not going to be defined wherever it is equal to 0, the denominator. So wherever the cosine is equal to 0, it's not defined, and therefore it will have a, it's undefined at that point, those points. So the tan function is continuous for all real numbers except pi over 2, negative pi over 2, 3 pi over 2, you're going all the way around, 5 pi over 2, 7 pi over 2, all the multiples where we're either at the top of that unit circle or the bottom of the unit circle, which is pi over 2, 3 pi over 2, 5 pi over 2, 7 over 2, all the odd numbers. So it says all the odd multiples of pi over 2. That is where the denominator is equal to 0, can't fly. And the other two that they mentioned in the section is that exponential functions is continuous. There's no gaps in this situation at all. Continuous on its domain, all real numbers. So exponential function, e to the x, anything to the x power, we've got a situation where it is continuous on all real numbers. Logarithms, on the other hand, you can't have a negative x value. You know, you can't, 10 to no power gives you a negative answer. E to no power gives you a negative answer. So as a result, ln of x can't be, you know, the x value can't be negative, but it's positive. So the way they state that is a logarithmic function is continuous on its domain, all positive real numbers. The domain of the log functions is positive. All right, so those are the key points of section 1.4.